Hello elements, welcome to Unit D Review Podcast. Unit D is Chapter 10, 11 and 13. Chapter 10 is gases, 11 is IMFs and 13 is solutions. So let's look at each of these in detail and see how we identify each of these and what are the main concepts. So Unit D review. Let's start reviewing Unit D with solutions. Remember, at the heart of solutions are two components, solutes and solvents. The component that's present in smaller amount is called solute, and the component that's present in larger amount is called solvent. So with solutions we have reactions. Solutions react. And the three type of reactions that are based in solutions are called as precipitation, acid-base, and redox. Even though there are other types of reactions like decomposition, synthesis, they don't necessarily have to be in solutions. Hence, we haven't included that here. Now, when you write reactions, remember in APChem, we always write balanced net ionic equations. And to be able to write net ionic equation, what you need is solubility rules, because solubility rules tell you which ionic compounds will dissociate and which will not. Even for ionic compounds like NaNO3 that can dissociate in aqueous solutions, if a reaction says you have solid NaNO3, this will not dissociate. So I want you to read the question carefully. Just because you see an ion that can dissociate, don't automatically dissociate it. Ponder over its state. Is it in aqueous state or is it solid? So we'll talk a little bit more about it when we talk about reaction prediction. But for now, acid-base reactions give you, or you can figure out acid-base reaction, the quantitative aspect of it using titrations. And the basic concept of titration is at the end point, moles of acid become equal to moles of base. And then the redox titrations, you need to know oxidation states. You must know your oxidizing agent, reducing agents, and how we balance redox reaction is using half reaction method, where you balance the electrons that are given off by one half with the electrons that are accepted by other half. And I'm going to deal with it in Unit F. Now, talking about solutions, there is a process of dissolution or process of solution. Now, process of dissolution, the basic concept there is like dissolves like. And what that means is if you have a polar compound, it will dissolve a polar solute in it. If you have a non-polar solvent, then a non-polar solute will dissolve in it. And with the process of dissolution, with the solutions also come stoichiometry. And stoichiometry refers to quantitative analysis based on balanced mole ratios. So when we talk about process of dissolution and like dissolves like, we need to pay attention to the nature of solute. And solute can be electrolytic or electrolytes and non-electrolytes. Electrolytes are the solutes that dissociate, and non-electrolytes do not dissociate. So what are electrolytes? Generally your strong acids. Remember your 7 strong acids. What were they? HCl, HNO3, H2SO4, HBr, HI, HClO4, 1, 2, 3, 4, 5, 6, and what am I missing? HCl, HNO3, H2O, so 4 HBI, Br, HI, HClO4, HClO3. And then your strong bases are electrolytes, so these are the group 1 and 2 hydroxides. Electrolytes means they will be dissociated when you write net ionic equations. And also electrolytes are your ionic compounds that solubility rules dictate that they will dissociate. Now, in terms of stoichiometry of the reactions, you have various quantities to measure the strength of a solution. The first and the most common measurement is done using mass percent. Mass percent generally is either can be mass over mass, could be volume over volume, or mass over volume. Okay, this is not molarity over volume, mass over volume, so like grams per ml. Okay, so generally when I say 5% weight by volume, so it means 5 grams in 100 ml of solution. That's how mass percent works. It means either the mass or volume per 100 grams or 100 ml, depending on what quantity you're using. So denominator is always 100 and numerator is always 1. Then the second concentration unit is molality, and molality is moles of solute per kilogram of solvent. And molality is used in freezing point, depression, boiling point, elevation, all those, and osmotic pressure, boiling point, elevation, and osmotic pressure, or all the colligative properties. Molarity is used, the next quantity is molarity. It is moles per liter of solution, and molarity changes with temperature. So any place where you're changing the temperature, molarity is not a good quantity to use. That's where you use molality. And the last part about stoichiometry is dilution. And while you dilute solution, you use M1V1 is equal to M2V2. Two things to keep in mind while diluting. The first thing is AAA. Always add acid to water while diluting. Acid to water while diluting. Also, as you're using M1V1 is equal to M2V2, keep in mind that V2 is the final volume of solution. So sometimes the question will ask you how much water should be added to make 0.1 molarity from 2 molarity solution, right? So if they're asking you for water, that answer will be different than the total volume of solution. So keep that in mind. And last little bit of comparison between molality. Can you tell me between 1 molar aqueous NaCl and 1 molar aqueous NaCl, which one is more concentrated? And the answer is 1 molar. And we've gone over it at least 4 times in class, so by now you should know why. Let me see, what did I miss here? Am I missing anything here? I think that pretty much sums it for solutions. Now I'm going to move on to gases. So gases are a state of matter, and they have their own special nature. And gases nature is that they are made up of small particles, and there's a big space between particles. So most of the space in gases is empty. They're particles, so most of space is empty, and particles are constantly moving in rapid random motion, and intermolecular force between particles is negligible. Okay, and these describe the properties of a gas. And this is, all these postulates come from a theory which is called as KMT, or Kinetic Molecular Theory of Gas. Kinetic Molecular Theory of Gases gives a theoretical basis for explanation of behavior of gases. So like in solutions, you measure the concentration of solution by molarity, mass percent. The gases concentration, if I may use that word, is measured by pressure of gas. Generally, how much gas particles are present is measured by the pressure that gas exists. So pressure of gas is measured or defined as force per unit area, and there are various units for measuring the pressure. The three most common units are ATM. Remember, our atmospheric pressure is 1 ATM, or torrs. 760 torrs is 1 ATM, or millimeters mercury. 760 millimeter mercury is 1 ATM as well. So millimeter mercury and torrs are equal units. And then there is kilopascal or pascal. A kilopascal is 1.01 times 10 power 5 pascal is 1 ATM. So these are the conversions you must remember for various units. And the devices that measure pressure are called manometer and barometer. Barometer measures atmospheric pressure, while manometer measures pressure of a gas. And there are U-tubes involved in manometers. Open end manometer versus closed end. Closed end, just the difference of the two columns gives you the pressure of the gas. In open end, you have to factor in atmospheric pressure as well. Now, gases obey certain laws, and we call them gas laws. And there are 5 gas laws that the gases obey. And these laws are Boyle's law, Charles' law, Avogadro's law, Dalton's law, and Graham's law. Boyle's law says that pressure and volume are inversely proportional, or product of pressure and volume is constant. Charles' law says ratio of volume and absolute temperature is a constant. Avogadro's law says that 1 mole of a gas occupies 22.4 liters at STP, or volume is directly proportional to moles of gas. And Dalton's law says if you mix a number of gases, then the total pressure is equal to the sum of the partial pressure of gases. And Graham's law deals with the effusion, and I'm going to go over it in a minute. So all of the first 3 laws combine together to give ideal gas law. Ideal gas law applies to ideal behavior of gases, but please note that only a few gases exhibit ideal behavior under normal pressure and temperature. Ideal gas law is PV is equal to nRT, PV nert. And ideal gas law uses R, or universal gas constant, and its value is 0.0821 liter atmosphere per Kelvin mole, which we use in terms of gases, or we use 8.314 joules per mole Kelvin, and we use it in terms of wherever energy is used, like activation energy, in Gibbs free energy, and all of those we use that value. Now, ideal gas show deviation from ideal behavior under normal pressure and temperature. The deviations are greatest at low temperature and high pressure, because at low temperature and high pressure, the two assumption that there's a negligible intermolecular force and the volume occupied by gas particle in relation to overall volume is zero, both of these assumptions don't hold good, and hence gases deviate. And to account for these deviation, van der Waals equation was used, and it was P, just a second guys, P plus n square A over V square V minus NB is equal to nRT. So for ideal gases, you add a little factor to account for the loss of pressure due to intermolecular forces, and the volume you take away a certain factor so that your real gases can be closer to ideal gases. This is van der Waals equation. A and B are constants, and these can be experimentally calculated for each type of gases. Generally they are given to you. You need to know how to apply it in this equation. Then the next part here is, I'm going to go back to the ideal gas equation. It can be written in two other forms. PV is equal to nRT is the most common form. D is equal to PM over RT. It's just rearranging it. This version of ideal gas equation is used when you're calculating density of a gas. And M is equal to dRT over PV. This is to calculate M, or the molar mass of a gas. Now, when you are trying to figure out the stoichiometry of the gases, I'm going to write it here. In gas stoichiometry, it's very simple, guys. There are only two things that you have to consider. Is it a STP problem or a non-STP? If it is non-STP, then you use ideal gas law. If it is STP, then you know that 22.4 liters of that gas will occupy 1 mole, 1 mole of a gas, any gas will occupy 22.4 liters. The only other thing you need to remember in terms of stoichiometry is collection of gas over water. When you collect gas over water, water vapor sneaks in along with the gas. So the pressure that you read is not only of gas, but is of gas and water vapor. To figure out the pressure of gas, you have to subtract water vapor pressure, and this you can find from a chart at the back of your book, or generally it is given in the problem. And another thing about gas stoichiometry is sometimes they'll give you a solid in there. Remember, gas laws are obeyed only by gases. So if they are asking you for moles of solid, first you have to figure out moles of a gas, and then using stoichiometry convert it to solid moles. You cannot apply gas laws to solid moles. Now the very last part of gases, and I'm going to scroll down and lose my writing, is dealing with KMT again. And so I am somewhere here when I'm talking about KMT, so I'm going to scroll down. KMT. And With KMT, we talk about kinetic energy of gases. And remember, how did we calculate kinetic energy of gases? Is equal to, kinetic energy is equal to half mu/rms squared, where urms is root mean square velocity. The thing that you got to remember is this mass is in kilograms. Okay, and the formula for urms is square root 3RT over m, where m is molar mass and this is in kilograms as well. One thing I want you to remember, that average kinetic energy is same for different gases at same temperature. Now please listen carefully here. Even though average kinetic energy is same, it doesn't mean that all particles are moving at the same velocity. The particles may move at different velocity. Their average velocities are the same. Also, because average kinetic energies are the same, if you have two samples, let's say at 20 degrees you have hydrogen and argon, will their particles be moving at the same average speed? No. Hydrogen particles will be moving faster because they are lighter as compared to argon. Okay, so keep these things in mind. And with that comes the Maxwell's distribution curve. So this distribution curve, I'm going to draw 3 lines there. Here, as you increase the temperature, so generally it is between number of gas particles, and you have temperature on the x-axis, and the number of gas particles are shown by the shaded region under here. So so here is oxygen at 273, and then you have oxygen at 1000 degrees, and then you have hydrogen at 1000 degrees. So the lighter the particle, the faster it moves, and when the gas particles are moving faster, the curve shifts to right, because then you have a lot more particles with higher velocity. So you have velocity and number of particles on the y-axis. So between hydrogen and oxygen, if you compare at a certain velocity, hydrogen has all of these particles that have higher than that velocity, while oxygen just have these many particles. Okay, so as the particle speed, molecular motion, particle velocities increase, the curve shifts to right. And with that, we have just to go over intermolecular forces in Unit D review. And intermolecular forces, even though they seem very simple, I think you keep going in circles with that, so I'm going to emphasize intermolecular forces. So there are intermolecular forces, London dispersion forces, hydrogen bond, dipole-dipole interactions, ion-dipole, and sometimes ion-ion. Okay. London dispersion forces occur in non-polar substances. So London dispersion forces are present in everything, but they are the weakest type of force. So if any other intermolecular force is present, generally London dispersion forces are not considered a major player. Hydrogen bonds occur in substances where hydrogen is attached to N or F or O. And on the other side, it has another electronegative atom that it can attract the positive charge of hydrogen to. Dipole-dipole is almost like hydrogen bond, but it is between two polar covalently bonded molecules. So hydrogen bond is almost like an extreme case of dipole-dipole interaction. And ion dipole is like if you dissolve an ionic compound in water. So that's ion dipole interaction. Okay. In terms of relative strength, this is the strongest, number 2, number 2, number 3, and number 4. Guys, remember, when you are melting ice, so these are your water molecules. When you are melting ice, you are breaking hydrogen bonds that are represented by the red lines in between molecules. When you're melting ice, you are not separating HO and H atoms from water molecule. You are not breaking the covalent bond. Please distinguish between the two. And that wraps up Unit D review. Thank you for listening.